Hello everyone, welcome back to another Watch Me Do Math video. In today's video I'm going to be doing an integral that my friend sent me, and it's an indefinite integral of dx over 2 plus cos 2x. So you can pause the video and try it yourself, but this is with one added condition, that you must use the substitution s is equal to, or say u for instance, is equal to tan x. So the first thing I thought to do is think about how I could possibly cram this substitution in there. If I was going to make this u-substitution, differentiating this equation, we find du over dx is equal to sec squared x, or du is sec squared x dx. If I wanted to make this substitution, I'd need to find a term of secant squared x in this original thing, in the original integral. But naturally, I can't actually find that. So how can I convert this integral into having some form of secant squared x? Well, if you have something you want to stuff into an integral, you can multiply the integral by 1, which is just going to be secant squared x over secant squared x, because anything over itself is 1, right? So if you multiply this into the original integral, then you won't actually be changing the thing inside, but it may allow you to manipulate things more easily. So you find secant squared x dx over 2 secant squared x plus secant squared x cos 2x. And of course that doesn't help us so much. It would be nice to be able to put this in neater terms. So secant squared x and cos 2x, how do we work with this? Well, we know that cos 2x is sine squared, cos 2x by the double angle identity must be cos squared x minus sine squared x. And say we multiply this by secant squared x. Well, it goes very neatly into cos squared x, because obviously secant squared x is 1 over cos squared x. And multiplying those two together, you just get 1. But for this, in terms of sine squared x, well, you get minus tan squared x at the bottom. And I suppose that is helpful, because you're going to be substituting u equals tan x anyway. So perhaps we could follow with this, perhaps we could use this substitution, but at the same time, we'll be left with this secant squared x over here, which may be a little more annoying to deal with, because we need to do more conversion steps to get to the final answer. So have an alternate form of cos 2x that doesn't include a sine squared x. But we know that cos 2x is going to be 2 cos squared x minus 1. Because sine squared x is 1 minus cos squared x. So if we make that substitution, you get this expression 2 cos squared x minus 1. And multiplying that by sec squared x, we get 2 minus sec squared x. So overall, you're left with the integral of secant squared x dx over, if we take the substitution, cos 2x is 2 minus secant squared x, 2 secant squared x plus secant squared x cos 2x, which is 2 minus secant squared x. And if we cancel out these secant squared x terms, we get secant squared x dx over secant squared x plus 2. So where do we go from here? If you are familiar with your trigonometric identities, this may be a fairly easy integral for you to do at this point, because you may recognize that secant squared x can be split into a one term and a tan squared x term. That's actually quite a useful tool. If you find any integral with secant squared x, or tan x, or something along those lines, you should always consider whether you're able to do anything with that identity, the 1 plus tan squared x equals secant squared x, or its sort of opposite, that is, actually never mind, I'm not going to go into that. You can often get a lot of stuff done by making that substitution. So if secant squared x is 1 plus tan squared x, the integral goes to secant squared x dx, which we know is du from our earlier working, over secant squared x plus 2, which is 2 plus 1 plus tan squared x, or 3 plus tan squared x. And overall, because tan x is u, as we were going to make the substitution earlier, we find it's just an integral with respect to u, 1 over u squared plus 3. So how do we deal with such an integral? What I have heard before is that when you are working with this kind of arctan style integral, it is often helpful to start with arctan and differentiate to get to here. So if we know that arctan x goes to 1 over 1 plus x squared when you differentiate, then perhaps we can draw some insight about this u squared plus 3. Because if we somehow made this 3 term into a 1, it might become more obvious, because making it into a 1 would make the form of the integral more similar to this differential of arctan x, or in our case, arctan u. And it might allow us to make a guess as to what is inside this arctan function to give us a u squared plus 3 on the outside. Of course, I know this, but I want to work through my thought process in front of you guys so that it's more helpful to those of you who want to know how to solve similar integrals in the future. So this sort of technique of working backwards from arctan x's differential is fairly useful, and it may help you in the future. So suppose we want to get rid of this 3. Well, we can do that by multiplying both sides by 1 again, but instead of sec squared x, it's a third. And that makes this integral the integral of 1 over 3 times, with respect to u, 1 over 3 times the integral with respect to u. This numerator goes here. The denominator is going to go to the inside. U squared over 3 plus 1. Or you could think of this as u over root 3 squared plus 1. 1 over that with respect to u. 1 over 3 times that. And what happens if we actually take, then, u over root 3 into this arctan x and differentiate it? Well, the chain rule will suggest that we multiply by a factor of 1 over root 3, and then differentiate with respect to u over root 3, meaning that you get 1 over u over root 3 squared, taking the place of x, plus 1. So d by du of arctan u over root 3 equals this. Or in other words, if you wanted to multiply both sides by 1 over root 3, you would get this 1 over 3 outside, which is what you want in the end. So d by du of 1 over root 3 arctan u over root 3 is equal to 1 over 3 times 1 over u over root 3 squared plus 1. And ultimately, this is the expression we're looking for. That's the thing that's in our original integral. So this is sort of a rule you can actually memorize. If you ever come across an integral in the form 1 over x squared plus a, or a squared is how it's often written, you may find that the integral of this is just 1 over a arctan x over a, where a is the square root of the constant term in the system. And it is a pretty damn useful integral to memorize, if I'm going to be honest, because this integral does come up often as far as I've seen in IB exams. So d by du of times 1 over root 3 arctan u over root 3, and by the way, I was able to put this constant within the differential because if you multiply a function, then clearly the things on either side of the function are also going to be multiplied by the same amount, meaning that the gradient is going to be multiplied by the same amount. It's sort of how you vertically stretch a function, you're also vertically stretching its gradient, which means that you're allowed to put factors in and out of differentials as you please, which is a helpful thing. And it also applies to integrals. And it's kind of the problem-solving technique that I was using here. The integral of the whole thing must be 1 over root 3 arctan u over root 3. And of course, using the substitution u equals tan x, this becomes tan x over root 3 plus c. And that's it. So if you enjoyed this integral, if you enjoyed the video or found it helpful to you in preparing for your IB exams or A-level maths exams, then do be sure to subscribe, like, leave a comment, perhaps email me at watchmedomath@gmail.com if you have comments and criticism or want some help. And until next video, thanks for watching.